Okay, so let's look at an example of circular motion in action. We have a vertical circle here. There's an object which is being whirled around a vertical circle, and let's make it go this way. It's going up the top and all the way around to the bottom again. So I'm interested when the object is at the top and when the object is at the bottom. And I'm going to draw the direction of the force that's acting on this. Well, there's only one force, and that's our centripetal force, which always acts towards the centre of the circle. Okay, so this is our sort of horizontal position, and here we've got top and bottom. So we know that the centripetal force is m omega squared r, and incidentally we derived that equation as well, didn't we? So we can make omega equal to v over r, and if you substitute v over r for our omega squared, you can get another equation for centripetal force. I'm going to put little c's on this so we know what we're talking about, and that will be m times v squared over r squared times r, which is going to give me mv squared over r. So that equation and this equation are equivalent. So it's often best to work with this one because we're often given values for v, not omega, which makes our lives a little bit easier. Otherwise you have to work out what omega is, which is fiddly. So let's try using this one. So let's remember what this means. This is the resultant force, and so our resultant force is always acting towards the centre of the circle given by these arrows, and so we have to consider all of the forces acting to make up this resultant force. Now clearly there's a tension force when you're pulling on the string to make this object go in a circle, but also there's the weight force of the actual object itself. So if you look at the top situation here, just look at the top, you've got a force acting down there of weight, and you've got the force of tension, and those add together to give you the total resultant force, which is Fc. So the top. So top, I've got forget that. At the top, we've got the resultant force Fc is equal to mv squared over r, which is equal to the tension force plus the weight force. I think you can see what's going to happen at the bottom. The weight force is acting downwards at the bottom, and our tension force is acting upwards. Okay, bottom. Centripetal force is still equal to mv squared over r. That's the same. But this time we've got the tension force at the bottom, and we're going to minus the weight from it because it's going in the opposite direction to the centripetal force. So if you rewrite the equations now for top and bottom for tension, you can see that the tension at the top will be equal to mv squared over r minus the weight force, and the tension at the bottom is equal to mv squared over r plus the weight force. In other words, the tension at the bottom is greater than the tension at the top. Interesting, isn't it? So if this is a weak piece of string and you're whirling a heavy-ish mass, it's more likely to break when the mass reaches the bottom of the swing than it is at the top.